Welcome to this poster presentation brought to you from Edinburgh Instruments in collaboration with GMP, detailing the use of Raman microscopy in the food and drinks industry. We will briefly introduce 4 different applications within the industry, and if you're interested to know any more about them throughout the presentation, QR codes will be displayed, which when scanned will take you to the application notes available on our website. Let's get started by discussing pesticide detection. Pest infestation is a massive issue for the global food supply chain. Chemicals called pesticides are one tool which can be used to combat these issues. However, they can be harmful to both the environment and human health. A commonly used pesticide on apple trees, for example, is Fosmet, which is used for controlling codling moths. Whilst the apples should be thoroughly cleaned, there is the risk of residual pesticides remaining on the apple skin, which could cause harm to human health. As such, regulatory bodies have set safe tolerance levels for each pesticide. Fosmet has a level of 10 parts per million, or ppm. One technique which can be used to detect these low concentrations of Fosmet is surface-enhanced Raman scattering. SURS offers increased scattering intensity by using nanoparticles in close contact with the sample. There are many commercially available SURS substrates on the market. To highlight the sensitivity of SURS to these low concentrations of Fosmet, a piece of apple skin was spiked with 1 ppm Fosmet solution, which in fact is lower than the 10 ppm concentration set by regulatory bodies. The apple skin was then swabbed and placed into a solution of water, which was then pipetted onto the SURS substrate. This was placed directly under the Raman microscope for analysis. Firstly, I would like to highlight the effects of SURS. The 10 ppm solution of Fosmet was analysed by itself and on a SURS substrate. Without SURS enhancement, there are no Raman peaks visible. However, on the substrate, we see strong and well-resolved Raman peaks. Further, when we analyse the solution that was gathered from the apple swab, we can clearly see well-defined peaks that are easily identified as Fosmet. As well as detecting harmful materials, another issue in the food and drinks industry is fraud. We'll talk about edible oil fraud in this example. One issue we see is the adulteration of high-quality oils with cheaper ones, such as extra virgin olive oil with rapeseed oil. This obviously has the commercial issue of falsely selling a product, but it can also carry human risk, such as a case in Spain where oil that was meant for industrial use was being sold by vendors as olive oil, and it actually resulted in 300 deaths. So being able to detect the oil is legitimate is crucial both for the industry and for safety. To demonstrate how Raman spectroscopy can be used to help with this problem, 6 supermarket oils were analysed and 2 adulterated oil samples were made containing 50% extra virgin olive oil and 50% olive oil or grapeseed oil. Visually, the spectra appear identical. So whilst we get strong Raman responses, by eye we cannot tell the difference from the spectra of every oil type. So what do? Well, thankfully we can employ multivariate analysis. In this case, we've used hierarchical cluster analysis, and this essentially can be thought of a family tree of relatedness. So first of all, we get 2 clusters separating out any samples with grapeseed oil in it from those that do not contain grapeseed oil. And then as we work further down this tree, we can see that we can even separate out the 2 adulterated samples. Now let's move on to the drinks industry, which is a massive industry bringing in high amounts of revenue, meaning it's susceptible to fraud. Focusing on spirits, and specifically whisky, since we're a Scottish company, we'll discuss 2 types of fraud. Firstly, the watering down of alcohol with water in order to make more profit, So this means that the percentage ethanol marked on the bottle that you've bought is actually inaccurate and there is less ethanol in that bottle than stated. Further, alcohol is sometimes illegally manufactured, which means it doesn't pass through the regulatory checks and may contain methanol. Whilst ethanol is consumable by humans, methanol is toxic and is commonly found in antifreeze. Tackling the first problem, we can use Raman in a quantitative way by making a calibration curve of ethanol at different concentrations. We do this using the peak at 880 wave numbers, as it behaves linearly with increasing concentration. We can then measure 3 whisky samples, 2 of which were straight from the bottle and 1 was diluted. The 2 that were taken directly from the bottle clearly show the correct ethanol percentage that's marked on their label. The sample, which we diluted, clearly has a lower ethanol percentage, and thanks to the quantitative power of Raman, we can now say it was 33% ethanol. Moving on to how we can use Raman in a qualitative manner, we work on the identification of methanol. So whilst methanol and ethanol are very chemically similar, they produce significantly different Raman spectra. Focusing on the Raman band at 1035 wave numbers, we can see this is only present in methanol and the whisky sample spiked with methanol. The peak is completely absent from the whisky sample and the ethanol sample. The previous 3 examples have highlighted how useful Raman spectroscopy is in the food and drinks industry. However, what else can our Raman instruments offer you? Well, they're coupled to confocal microscopes. Thanks to this coupling, we can now perform Raman mapping. In Raman mapping, the sample is visualized underneath a microscope, and a grid is set up over the sample area to be mapped, with the user determining the step size, i.e. how often to take a Raman spectrum. This allows distribution studies, as we can now visually see areas of our sample and what they are. Distribution studies are important in many fields, for example in the pharmaceutical industry, to determine where the active ingredients are. In the food industry, we've taken a sample of white chocolate. White chocolate is composed of 3 main components: lactose, fat, and sucrose. Using Raman mapping, we can collect millions of spectra, which can be characterized as one of these 3 components. We can then color areas which have spectra matching each component to see the distribution of them in the sample. So for example here, we can see where the sucrose is located or where the lactose is located. To conclude, Raman microscopy is an extremely useful analytical technique across the food and drinks industry. It helps to ensure the legitimacy and safety of products whilst also allowing distribution analysis. If you'd like to know more about the presentation today, the QR codes throughout will take you directly to the application notes on each subject. And if you want to know how we can help with your application area, please get in touch with our sales team who'll be happy to discuss how we can help elevate your laboratory.